VLSI టెక్నాలజీకి సంబంధించి ఎట్లా ఉంటుంది, ఇండస్ట్రీకి ఏ విధంగా ఉపయోగపడుతుంది, దానికి సంబంధించిన వివరాలు ఈ ప్రోగ్రామ్ను ప్రతి శనివారము ఈ టీశాట్ ద్వారా నిర్వహించాలనుకుంటున్నాం. ఎందుకంటే టెక్నాలజీ వల్ల ఎట్లా ఉద్యోగాలు వస్తాయి ఐటీ కంపెనీల్లో, దానికి సంబంధించి VLSI నేర్చుకోవాలి అంటే చాలా కాస్ట్ ఉంటుంది. కాబట్టి ఇది టీశాట్ ద్వారా ఇది అందరికీ చేరాలని చెప్పి ఈరోజు ఈ ప్రోగ్రామ్ను స్టార్ట్ చేయబోతున్నాం. మై సెల్ఫ్ వేణుగోపాల్ రెడ్డి టీశాట్ CEOగా ఈ ప్రోగ్రామ్ను ఇక్కడ కండక్ట్ చేస్తున్నాం. ఇది ఇవాళ డిప్యూటీ సెక్రటరీ భవేష్ మిశ్రా గారి చేతుల మీదుగా ఈ ప్రోగ్రామ్ను స్టార్ట్ చేయబోతున్నాం. భవేష్ మిశ్రా గారు, అదేవిధంగా పొటానిక్స్ వ్యాలీ కార్పొరేషన్ ఇన్ఛార్జ్ రవీంద్ర రెడ్డి గారు ఉన్నారు. మొత్తం ఈ పొటానిక్స్ వ్యాలీ కార్పొరేషన్ ద్వారానే ఈ ప్రోగ్రామ్ మేము నిర్వహిస్తున్నాము. సో ఇప్పుడు సంబంధించిన వివరాలన్నీ కూడా
టుడే we are going to launch about the VLSI awareness program. This will be helpful to all the EEE and ECE students where they can decide their VLSI career. So officially speaking, what exactly is the VLSI? Very large scale integration. So when you started the career and when you started the VLSI, so it integrates multi-millions of transistors. It starts from hundreds, thousands to millions to now it came to billions of transistors on the CMOS process. CMOS is complementary metal oxide semiconductor. So in this course, every student can decide on the career. So when they want to decide in the front end or back end. In the front end, what are the different techniques, what are the different logic, it varies. And when it comes to back end, what exactly is the place and route and where these fabricated chips and exactly is going to decide. So in the VLSI awareness program, you are going to learn about topics on DFT, logic synthesis, place and route, DFT and STA and fabrication process. The industry experts are going to talk about this program on every alternate Saturdays from the TSAT. This is a collaboration program from Photonics Valley Corporation, which comes in ITEC department, Government of Telangana, along with TASK and ASIP technologies and TSAT. This collaborative program is for the awareness about the VLSI program. So
scientist co-founder of Intel. So ఆయన ఇచ్చారు దట్ ప్రతి 2 years లో ఒక ఏరియాలో మనం పెట్టే ట్రాన్సిస్టర్ సంఖ్య డబుల్ అవుతా ఉంటుంది. సో దాన్ని మనం 3లా ఉంటాము. సో దానివల్ల ఏమైంది అంటే ఇంతకు ముందు ఒక చిప్ కి ఒక 5 మైక్రోమీటర్ కానీ నానోమీటర్ సైజ్ ఉంటే ఇప్పుడు 3 నానోమీటర్ అయిపోయింది. సో ఇప్పుడు మనం 3 నానోమీటర్తో చిప్ని తయారు చేస్తున్నాం. సో జనరల్గా పిల్లలందరికీ స్టూడెంట్స్ అందరికీ మన ఈ పైథాన్ ప్రోగ్రామింగ్ లాంగ్వేజ్, జావా స్క్రిప్ట్ ప్రోగ్రామింగ్ లాంగ్వేజ్ అట్లాంటి ప్రోగ్రామింగ్ మీద అవగాహన అయితే ఉంటుంది, కానీ VLSI మీద అంత అవగాహన ఉండకపోవచ్చు. కానీ ఇప్పుడు టాప్ 10 వస్తే దాంట్లో నెంబర్ 1 కంపెనీ వచ్చేసి NVIDIA. సో NVIDIA బేసిక్లీ ప్రిపేర్స్ చిప్, మనం GPU అంటాం. GPU చిప్ ని మనం AI కోసం వాడుతూ ఉంటాము. సో మనం ఇప్పుడు మనలో చాట్ GPT కానీ వాడుతూ ఉంటాం. ఉదాహరణకి వాట్సాప్ ఇస్తే వాట్సాప్ బాక్స్ లో కూడా పైన అండ్ సర్చ్ విత్ AI అనేది వస్తుంది, మెటా AI వస్తుంది. దాంట్లో మీరు క్లిక్ చేసిన తర్వాత బ్యాక్ ఎండ్ టెక్నాలజీలో GPU. ఈ GPU అనేది టెక్నాలజీ మనం ఎట్లా తయారు చేస్తాము, దాని వెనుక ప్రాసెస్ ఏంటి, టెక్నాలజీ ఏంటి, దాని VLSI టెక్నాలజీ అంటాం. అంటే వెరీ లార్జ్ స్కేల్ ఇంటిగ్రేషన్. ఈ ఎలా తయారు చేయాలి, ఇప్పుడు మనకి ఏ కంపోనెంట్స్ గేట్స్ అంటాము జనరల్గా ఎలక్ట్రానిక్ భాషలో. ఇట్లాంటి మనం గేట్స్ అంటాము. ఆ గేట్స్ ని మనం అసలు చేసి డిజైన్ తయారు చేసి సెమీకండక్టర్ ఫ్యాబ్ కంపెనీ అంటాం. కంపెనీకి మనం పంపిస్తే ఆ కంపెనీ నుంచి చిప్ అనేది వస్తుంది. సో 1970s, 80s, early 2000 వరకు భారతదేశం పెద్ద ఇంటిగ్రేటర్ ఫెసిలిటీ లేదా ఉండే. ఇప్పుడు మన హైదరాబాద్ సంఖ్య చూసే పెద్ద కంపెనీస్ అది కావచ్చు, AMD, క్వాల్కామ్, సినాప్సిస్, ASIP, అన్ని కంపెనీస్ కి రీసెర్చ్ సెంటర్స్ వాళ్ళు ఓపెన్ చేసి. సో మన తెలంగాణ అయితే దీంట్లో ఒక మంచి భవిష్యత్తు కూడా ఉంది. ఒక రీసెర్చ్ ప్రకారంగా మన సాఫ్ట్వేర్ ఇండస్ట్రీలో మనకి ఎంత అయితే శాలరీ వస్తుందో ఈ సెమీ కండక్టర్ ఇండస్ట్రీలో మనకంటే అట్లీస్ట్ 3 times మీకు ఎక్కువ శాలరీ కూడా వచ్చేస్తుంది. అండ్ ఇట్స్ ఎవర్ గుడ్ ఫీల్. ఉదాహరణకి ఇప్పుడు ఇంతకుముందు భారతదేశంలో ఒక ఫోన్ మనం చైనాని వేరే దేశం నుంచి ఇంపోర్ట్ చేసేవాళ్ళం, కానీ ఇప్పుడు వెళ్ళిపోయింది. ఇప్పుడు యాపిల్ లాంటి పెద్ద కంపెనీ కూడా ఇండియా నుంచి చేస్తుంది. సో ఈ ఎలక్ట్రానిక్ సెక్టర్ లో మన హైదరాబాద్, బెంగళూరు, తమిళనాడు ఇట్లాంటి ప్రతి సిటీస్ లో సెమీకండక్టర్ నౌ హ్యాస్ బికమ్ అ బిజినెస్. సో ఈ ఇంత పెద్ద తప్పనిసరిగా తెలంగాణలో చదువుతున్న పిల్లలు కూడా దీనికోసమే టీసీ డిపార్ట్మెంట్ ఫోటోనిక్స్ వ్యాలీ కార్పొరేషన్ ద్వారా VLSI మీద అవకాశం మన డిసెంబర్ నుంచి 12 April వరకు ఆన్లైన్ 2 ట్రైనింగ్ తీసుకోవచ్చు. అదే విధంగా ఈ VLSI సాఫ్ట్వేర్ కొంత ఎక్సెసివ్ ఉంటుంది. దీస్ ఆర్ లైసెన్సెస్ రూపీస్ పర్ ఇయర్. సో అకాడెన్స్ హైదరాబాద్ పిల్లలకి ఇష్టంగా ఆ సాఫ్ట్వేర్ యాక్సెస్ కూడా ఇస్తాం. సో నాకు తెలిసిన దట్ వాజ్ అ కోర్స్. 3 నెలల్లో నేను కూడా అకాడెమిక్ సాఫ్ట్వేర్ వాడాను. బట్ 3 months మనం దీని మీద కొంత శ్రద్ధ పెట్టి నేర్చుకుంటే తప్పనిసరిగా ఆఫ్టర్ 3 to 4 months ఒక బేసిక్ చిప్ డిజైన్ తయారు చేయడం మీకు ఈజీగా వచ్చేస్తుంది. స్టూడెంట్లు మార్కెట్ లో ఎక్కడ వెళ్ళినా ఒక మంచి జాబ్ దొరికే ఛాన్స్ ఉంది. సో దట్ ఇస్ ద
గారు ఫర్ యువర్ వాల్యుయేషన్స్ అండ్ ఫర్ ద ప్రోగ్రామ్. And simply if you say VLSI, right, it starts from RTL to design specifications and then RTGDS. So in terms of RTGDS, there are various subjects that are featured. So you will know about this awareness program, what is RTGDS, resonance and synthesis, and STA analysis, then comes to systems, and then comes to place and route, and the fabrication process. Today, the fabrication process, most of the fabrication is done through TSMC and USC and globally. They mostly exist in out of India. And the government of India very encouraging semiconductor field in Telangana and India. They are providing incentives to the startups, MSMEs, and they are providing free software as well. If some startup comes with proper design specifications and their design linked incentives are from the central government, and Telangana state also providing 20% subsidy in that field. And now I request Simhadri, who is a industry experts, is going to talk about the VLSI, and probably in the next training courses he will introduce the introduction of the VLSI. Now he is going to talk about today's program.
Hello everyone, this is Venkata Simhadri, CEO, Advanced System and Package Technologies. I take this opportunity to thank our Minister Shri Sridhar Babu Garu, Shri Baish Ranjan, IS Special Chief Secretary, Shri Baish IS Deputy Secretary, Shri Ravindra Reddy, Photonics Valley Corporation, Shri CEO Task, supporting this initiative with exposure to and opportunities. The good news is the industry continues to grow worldwide, and even though it may have occasional dips, the opportunities for chip design engineers will continue to grow. And traditionally, most of the engineering graduates in India, they look for jobs in either IT or software related fields. But for engineers with an engineering degree in electronics, electrical or VLSI engineering, semiconductor industry is a great opportunity to get in. It is a challenging field. You will continue to learn for the rest of your life, and it gives stability and also better salaries. So we are conducting 10 webinars, and it gives you a very good overview of the complete VLSI design cycle. These are webinars that give you an excellent exposure to the design cycle. And also let me tell you, these webinars will not make you a hands-on chip design engineers. This is just an exposure. You will need more detailed hands-on training to get into this field. It can be an MTech in VLSI design. It can be an entry-level position in a company that will give you more hands-on training. And also it can be a training institute. There are some very good training institutes even in Hyderabad that will provide you hands-on training to get into this field. So in addition, I also want to highlight what's happening in India. The government of India, under the leadership of our Prime Minister, Honorable Prime Minister Modi, and also support fabless product companies. So there is something called DLI scheme. So if you are a startup and designing your own chip product, the government is going to provide support. So in summary, if you are an engineering graduate with strong academic record and good fundamentals, semiconductor industry is a great opportunity to start your career. Thank you.
Thank you, Venkata Simhadri garu, for your valuable suggestions, and he is going to be in the training class for the next introduction period, in the next coming up period. Now I request Mr. Srikanth Sinha, past CEO, to talk about this topic.
A very good morning to all the management of different colleges, to all the corporates, to all the faculties, HODs of various engineering colleges and polytechnics, and dear students and all the dignitaries present over here today, especially Bhavesh Mishra Garu, Ravindra Reddy Garu, Venkata Simhadri Garu, and all others present today on this inauguration of the VLSI program, which is an initiative of the PVC, Photonics Valley Corporation, along with TASC and the industry. Under the vision of our Honorable Chief Minister and the Honorable IT Minister, the state is all set to grow in the semiconductor industry, which is the future. I think when people talk to me, I talk about that India has already missed the software bus, because today we are not producing people with a product mindset, but we are just producing people for the operations and services industry. It's important for us hence to be part of the semiconductor industry revolution which is happening today, and I'm extremely happy that today the government has given us the vision, government has given us the direction of how we can actually take advantage of this revolution that is happening. As all we know that in India itself by 2026 the semiconductor industry today, which is in its nascent stage, is expected to be $55 billion, which will go up to $110 billion by 2030, and that is the growth potential that Telangana can also become part of. Today when we look at it, the focus of the manufacturers, the electronics manufacturers, or the ESDM as we call them, the electronic system design and manufacturers that are present over here in Telangana, are facing a shortage of people in the semiconductor industry, because most of the people are rushing towards IT industry itself. Our aim through this program is to ensure that we are able to provide the right kinds of inputs to the students so that they can become part of this growing industry. Today we have players, all the large players are over here in Telangana, in Hyderabad. They have set up their either their R&D facility or their fab facility over here in Telangana, and of course manufacturing also. Whether it be AMD, whether it be companies like Micron, whether it be NXP, Samsung, Broadcom, Veda IIT, Moschip, all these companies are there. Radiant is there. There are so many companies which are into these technologies. They require the right ready manpower, and today if you look at TASC itself, TASC works with about 755 colleges across the state, out of which we work with 145 engineering colleges and 98 polytechnics, which gives us a large pool of students who can be nurtured, who can be trained to look at working in the semiconductor industry itself. As a first step, I'm extremely happy that under the industry academia collaboration itself, along with PVC, we are coming up with this industry academia relation, this program under the academia industry relationship, where what we will be doing is we are getting industry leaders to come in and actually help guide the students, and this is over a period. It will be run on every Saturday. On every Saturday will be done in the morning hours itself, where industry leaders will come and talk about and train the students on the various aspects of the VLSI industry itself. Because if we look at the semicon industry, there are three major things that come into play. The first is the fabrication, second is first should be the foundation, second is the VLSI, and third is the fabrication, and that is how the whole industry would play. As a first step, we are focusing on the foundation, because today you need strong foundations. Everyone should be able to understand the fundamentals. Fundamentals is most important, because technology is going to change rapidly. Unless until the foundation is good, people would not be able to benefit from it. So our focus will be on the foundation, and then we will move to circuit designs. So we'll be talking about logical design, we'll be talking about physical design, and there'll be also hands-on, which will be done later on, along with the industry support itself. I'm extremely happy to say that multiple industries, including some of the ones that I mentioned earlier, AMD, Veda IIT, MOSCHIP, ASIP, and many others have come to partner with this initiative and ensure that our students are going to benefit from it. Dear students, my humble submission to you is please join this in large numbers and ensure that you take the maximum benefit out of this program, because this program is intended to help you launch your career in the semiconductor industry itself. Today, Telangana is at the verge of becoming a leader under the vision and the guidance of the IT Minister and the Honorable Chief Minister, where Telangana can show leadership in semiconductor also. I welcome you to become part of this revolution, welcome you to become part of this initiative, welcome you to have a great career for the future in semiconductor industry itself, which is the rising industry in India today. I am hopeful that with the initiatives etc. that are run under the guidance of Honorable Special Chief Secretary Jayesh sir, and the Honorable IT Minister, more and more companies globally would find Telangana as the ideal place for setting up their venture. The biggest lacuna for any company to look at India and Telangana is the availability of the trained resources. We at TASC, along with the industry partners and PVC, have brought this program so that this is the first step towards a career in that direction, and also as a commitment to the industry saying that yes, we will be providing the right, ready, trained resources as, when, where the industry wants it. On that note, I would once again like to thank Bhavesh Garu for being part of this initiative and launching it and supporting us in this initiative, to TSAT for broadcasting this program, this very, very valuable program for our students so that it reaches each and every household of Telangana. We would also be broadcasting this, as you already are seeing today, on the TASC platform as well as the YouTube channel of TASC. I once again would like to thank all the industry partners. Without their support, this program would not have been possible, and wish all the students doing this program all the very best for the future. Thank you very much.
Thank you, Srikanth Sinha garu, for your valuable suggestions and inputs. And today, the IT Minister D. Sridhar Babu garu and Honorable Chief Minister Revanth Reddy garu, they want to industry ready talent to be ready. So in that way, we are creating this VLSI awareness program for all the EEE and ECE students, where they can decide how semiconductor field, which field they can enter, front end, back end, and various topics. So during your course, you are going to learn about the basics of your CMOS, fundamentals, resistors and transistor logic. So how these are applied into the industry. So industry awareness program. So you will get the guidance from the various industry experts, those who worked for 10 to 20 years on the different fields of VLSI, and you can choose your career where you want to enter in that field, specific to front end design, specific to architecture design, specific to RTL, or specific to your logical synthesis design. You can decide your career based on the awareness of this program. Now I request Mr. Venugopal Reddy, CEO, TSAT, to talk about this one.
Okay, thank you. మీరు ఈ VLSIకి సంబంధించిన టెక్నాలజీని TSAT ద్వారా ఈ ప్రోగ్రామ్ నిర్వహిస్తున్నందుకు మీకు కృతజ్ఞతలు తెలియజేస్తున్నాను. అయితే మీరు ఇక్కడ మేము ఒక రిక్వెస్ట్ ఏంటంటే బొటానిక్స్ వ్యాలీ కార్పొరేషన్కి వాళ్ళకి చెప్తున్నదంటే, మీరు ఈ ఆన్లైన్ ప్రోగ్రామ్ టెక్నాలజీని ఇవ్వడంతో పాటు కొంతమందిని స్టూడెంట్స్ని ఇక్కడ తీసుకొచ్చి, కొంత సీఈఓలు ఏదైతే మీరు కంపెనీకి సీఈఓలు చెప్తున్నారో ఆ సీఈఓలను తీసుకొచ్చి ప్రాక్టికల్గా చేయించండి. ప్రాక్టికల్గా చేయించడం వల్ల ఇది మరింత ఈజీ అవుతుంది స్టూడెంట్స్కి. సో మీరు ఆ ఫెసిలిటీ కూడా కల్పించడానికి మాకు ఎటువంటి TSATకి ఇబ్బంది లేదు. ఆ స్పేస్ ఉంది. ఆన్లైన్లో మీకు ఎన్ని కెమెరాలైనా ఇక్కడ పెట్టి మేము ప్రాక్టికల్గా చూపించడానికి కూడా మాకు ఇక్కడ అవకాశం ఉంది. సో ఆ ప్రాక్టికల్గా మీరు స్టూడెంట్స్ని తీసుకొచ్చి ఇక్కడ చేయగలిగితే అది మరింత ఈజీగా దాన్ని అర్థం చేసుకోగలుగుతారు ఈ టెక్నాలజీ అనేది నా యొక్క ఆలోచన. భవేష్ మిశ్రా గారు చెప్పాలి దాన్ని.
అంటే మీరు చెప్పినట్టు వేణుగోపాల్ గారు, మేము ఇండస్ట్రీ ఎక్స్పర్ట్స్ ఎవరైతే ఉన్నారో, అదేవిధంగా సిఇఓస్ ఇన్ ద ఫీల్డ్, అంటే హైదరాబాద్ మన ఈకో సిస్టంలో పెద్ద కంపెనీస్లో ఎవరైతే ఎక్స్పర్ట్స్ ఉన్నారో వాళ్ళందరినీ ఇక్కడికి పిలిపించి, అదేవిధంగా ఒక ఇంటరాక్టివ్ సెషన్, కొంతమంది పిల్లల్ని ఇక్కడికి తీసుకువచ్చి, స్టూడెంట్స్ ని తీసుకువచ్చి వాళ్ళ మనసులో ఉన్న డౌట్ వాళ్ళకి చెప్పాల్సిన కమ్యూనికేషన్ లాగా చేస్తే ఆ పిల్లలకి మాత్రం కాకుండా మిగతా ఎవరైతే ఆన్లైన్ ద్వారా మనం చూస్తున్నారో వాళ్ళకి కూడా అడ్వాంటేజ్ అవుతుంది. సో ఇట్స్ అ వెరీ వాల్యుబుల్ సజెషన్. సో విల్ డెఫినెట్లీ ఇంప్లిమెంట్.
ట్రైనింగ్ ప్రోగ్రామ్ కూడా ప్లాన్ చేస్తున్నాము, ప్రాబ్లీ ఇన్ January-February టైమ్ ఫ్రేమ్. సో దట్ VLSI ట్రైనింగ్ ప్రోగ్రామ్ ఈజ్ ఆల్సో గోయింగ్ టు బి లాంచ్డ్.
సో కొన్ని ఫోన్స్ వస్తున్నాయి, తీసుకుందాం మనం. స్టూడెంట్స్ నుంచి ఉన్నట్టుంది, కాల్ తీసుకుందాం. హలో హలో
హలో
చెప్పండి, ఎవరితో మాట్లాడాలనుకుంటున్నారు?
ఎవరిచ్చిన పలకండి.
ఓకే, మీరు క్వశ్చన్ అడగండి.
VLSI ఇప్పుడు చదువుకున్న స్టూడెంట్స్ కి ఇంటర్న్షిప్స్ ఏమైనా ప్రొవైడ్ చేయగలరా?
Internships అనే ప్రోగ్రాము త్రూ ఎనీ ఆఫ్ డిజైన్ కంపెనీస్ we can do that one, but before that one you need to be come up with your complete knowledge about the VLSI and electronics and concepts. మన హైదరాబాద్ లో వచ్చేసి మనకు సినాప్సిస్, AMD, ఇంటెల్, క్వాల్కామ్, మైక్రాన్, మాస్చిప్ అండ్ ఫ్యూ అదర్ స్టార్ట్అప్స్ ఆర్ దేర్ ఇన్ హైదరాబాద్ లో. సో వీటిని అప్రోచ్ చేసి మీకు వాళ్ళకి రిక్వైర్మెంట్ ప్రకారం ఇంటర్న్షిప్ కూడా ప్రొవైడ్ చేయగలుగుతాం.
అంటే any requirements for internships for students, they need to do any projects before you provide internships for them?
సో అవన్నీ మనకు MNC కంపెనీ వాళ్ళు డిసైడ్ చేస్తుంటారు. సో బేస్డ్ ఆన్ ద రిక్వైర్మెంట్ బట్టి మనం వీ క్యాన్ అప్రోచ్ దెమ్.
సో ఇది కాలేజ్ ద్వారా కొంత ఇంటర్న్షిప్ చేయొచ్చు కదా, అంటే కోఆర్డినేషన్ చేయొచ్చు కదా,
కోఆర్డినేట్ చేయొచ్చు. వాళ్ళ కంపెనీ వాళ్ళకి కూడా వాళ్ళ రిక్వైర్మెంట్ కొన్ని పెడుతుంటారు. దీస్ మెనీ స్టూడెంట్స్
రీజనబుల్ క్వశ్చన్, ఎందుకంటే కాలేజ్ ద్వారానే ఇంటర్న్షిప్ ను ప్రొవైడ్ చేయాలి.
ఎస్, సో వాళ్ళకి దే హ్యావ్ లిమిటెడ్ స్పేస్ అన్నట్టు, అందరికి తీసుకోకుండా కొంతమంది లిమిటెడ్ పీపుల్ గా ఉంటారు. వాళ్ళకి మాకు ఇట్లా రిక్వైర్మెంట్ ప్రకారం మేము ఇంటర్న్స్ ఇస్తున్నామని అనౌన్స్ చేస్తారు. సో వాళ్ళని డైరెక్ట్ అప్లై చేసుకోమంటారు. సో దే కెన్ డూ దట్ వన్. మనకు సెమీ కండక్టర్ ఫీల్డ్ వచ్చేసరికి ఇండియా ఈజ్ వెరీ లాగింగ్ ఇన్ దట్ ఫీల్డ్. We want to get into the top and we want to reach the up to the mark. మనము ఇప్పటివరకు అయిన సెమీకండక్టర్ ఫీల్డ్ లో మోస్ట్లీ వీ డిపెండ్ ఆన్ టాప్ ఫీల్డ్ ఫ్రమ్ USA and China and Taiwan. So Indian government is also encouraging to set up this semiconductor to make it up to the mark. So government of India is providing the effort to put it a special budget for that one, and they are providing a tool software and additional fields for the trainings purpose. And if someone is coming up with a startup, so they are providing EDS softwares which are expensive for any startup which cannot afford. They can get it the license for free of cost. So that need to be get it approved through DLI web scheme. So you can apply it online, or if there is any help that you require for this, you can approach Photonics Valley Corporation, ITEC department, Government of Telangana.
థ్యాంక్ యూ. మొత్తం మీద ఈ ప్రోగ్రామ్ను టీసాట్ ద్వారా నిర్వహించినందుకు, ఈ ప్రోగ్రామ్కు లాంచింగ్ ప్రోగ్రామ్కి వచ్చిన భవేష్ మిశ్రా గారికి, అదేవిధంగా ఇన్ఛార్జ్ రవీంద్ర రెడ్డి గారికి, ఇంతకుముందు మాట్లాడిన సీఈఓలందరికీ కూడా థ్యాంక్ యూ.
థ్యాంక్ యూ అండ్ బెస్ట్ విషెస్.
Welcome to the series of webinars we are conducting on VLSI design, and this is the first webinar in our series, and it gives you a very high level introduction to the SoC design, all the way from defining the spec for the design and taking it to the production. So let's begin with a high level understanding of what is an SoC. SoC stands for System on a Chip. Basically, it is an integration of all components, multiple components of a computing system into a single chip. Why do you do that? To reduce area of silicon, number one. So once you reduce the area of silicon, it will result in reduced cost of the chip. Similarly, reduce the power and then increased performance. So let's see how it happens. If you look at a desktop computer, probably 10-15 years ago, it had the same power of a smartphone in your hand today. So how, the computing, so much computing power incorporated into a handheld device today, all because of SOCs, by integrating more and more components into a single chip and optimizing them for area, power, and cost. So a typical components in an SOC are central processing unit, which is called CPU. And based on the application, it might have a GPU or a DSP, a digital signal processing unit, or an AI accelerator that become a common factor in most of the chips nowadays. And other things like, a networking processor, or maybe a, video, audio codec, things like that. And then every SOC needs some memory to process that, store and process the data as it needs. And it can be RAM, it can be ROM, and off-chip DDR controllers sometimes we use. And then the peripheral interfaces like PCIe, USB, or HDMI based on the applications. And every SOC needs some level of power management to optimize the power consumption of the chip. And as I said, connectivity modules. For example, an SOC in your TV, it will need a HDMI interface. Similarly, a chip that is going into a set-top box might need a Wi-Fi module in there. So these are different modules you keep integrating into an SOC, like storage controllers, and if the SOC talking to a sensor, sometimes it might need a custom cell, for example, a ADC, analog to digital converter, to talk to a sensor outside. So some examples of SOCs, Qualcomm Snapdragon, that used to get into tablets and other devices. Similarly, Apple's A series chips, NVIDIA's Tegra. So these are some examples. Here is an example of an SOC, a block diagram, how it looks like. So this was an SOC that was used in a still camera. And you can see that it has an ARM CPU, and then an image processing DSP, video processing DSP, and multiple interfaces to talk to various, for example, talk to an image sensor, from there interfacing to a TV or a touch screen, and also talking to a wireless connected to transfer your data in and out. Then next step, once you define the spec of your SOC, the next step is to sit down and define the high-level architecture, and followed by microarchitecture. So let's see what goes in there. So architecture definition, basically it's you start with the system requirements based on the applications. As I said, if it is an SOC that's getting into a smart TV, or an SOC that is getting into your Wi-Fi router or a set-top box, each SOC will have its own requirements. And first you, jot down all the requirements. And then the performance requirements. So based on the application, again, you define the performance metrics. How fast your SOC needs to be running at, what is the clock speed, and then the power consumption. So if the SOC getting into a smartphone, the power is very important. You need to optimize it for the power as much as possible to extend the battery life of your smartphone. Similarly, the connectivity needs, whether it needs a Wi-Fi connection, the chip, or a Bluetooth connection, or USB. And PCIe. Then the security features it needs, whether it needs any encryption and other things. Then in the end, your SOC needs to go and compete with similar products in the market. So the cost and size constraints is also very important. You need to sit down and identify those requirements as well. Then you start with a high-level architecture definition. As I said, every SoC needs some kind of CPU to begin with. And are you using an ARM CPU? People are talking about RISC-V nowadays, or an x86 type of a CPU. There used to be another CPU called PowerPC also. Then what are the other modules you need inside the SoC? You need some DSP blocks, or you need some GPU or AI accelerator. So these are some common examples. And then you see how much memory, on-chip memory you need for your cache requirements, storing the data while you're doing the processing. And it can be some SRAM, single port SRAM, or dual port SRAM, various kinds of memories you can use. And then the peripherals, what kind of interfaces you chip will be talking to, like UART, SPI, I2C, and GPIOs. GPIOs stand for general purpose IOs to get the data in and out. And then you also, every SoC needs some kind of high-speed interfaces based on the application, as I mentioned. See, every SoC nowadays, every device you use talks to, has an USB interface, whether for storing data, getting the data in and out, or even for charging. Now we're using Type-C USB port for charging your smartphones. Then you, based on the application, you need HDMI interface, PCIe interface. So there are various kinds of high-speed interfaces your SoC might need. Then we are talking about power management, whether the SoC gets into an idle mode or a low power mode when it's not processing, or whether any modules in the SoC, whether you want to kind of put them in a sleep mode or shutdown mode to optimize the power. So those decisions you have to make at the architecture definition level. And step 3 is, identifying all the functional blocks and IP selection. So nowadays nobody, designs every block that is used in the SoC by themselves. Most chip companies or SoC companies, they license the pre-existing, pre-designed IP blocks. For example, if you're using an ARM CPU, you can license that CPU from ARM and just drop it in your design. Similarly, if you have a PCIe interface in your design, you just license it from companies like Synopsys or Cadence and drop it in there. Then some SoCs need custom IP blocks. I kind of explained it earlier. If you, for example, if you SoC talking to a sensor, an embedded sensor, or some kind of a sensor outside the chip, and if the signal is coming in the analog format, you might need an ADC to convert that data into digital format and to process it. So sometimes you can license these IPs from third parties, or you may end up designing it yourself. Then you have to define how all these blocks are integrated on your SoC. Then all these blocks need to talk to each other on the SoC. Then there's something called system interconnect. There are people use, there are standards like AMBA, AXI, or you develop your own custom bus. And so these bus, basically, as I said, AMBA bus, it's based on determining the bandwidth you need, the latency and reliability requirements. And then if you have a data path in your design, you need to kind of define that and architect that as well. And most of the chips nowadays, they also use off-chip DRAM memory to store your data in and out. And so DRAM controllers, you may need a DRAM controller and DRAM interface on your chip. you need to define that as well. So as I mentioned earlier, so this is a block diagram and high-level architecture of an SoC that went into a digital camera. So, so this is the first thing they do, define the block level architecture of your SoC and identify all these blocks, where you're getting them and which ones you're designing them yourself and how they talk to each other. The next step in the design process is called RTL design. Once you identified and finalize the architecture of the chip, you get into the RTL mode, RTL design. So before we talk about RTL design, how it is done, let's go back and take a recap of the basic fundamentals of digital design. So any digital design typically has some combinational logic and sequential logic. And I'm sure most of the students here have learned these fundamentals in your undergraduation. So if you look at the combinational logic, the fundamentals start with Boolean algebra. Then you learn about logic gates. I'm sure you learned about De Morgan's theorem and how to do truth table and optimize the logic to get the most efficient gate level circuit for the logic. Here is a simple example of a 3-input adder and how it is defined in a truth table and the derived gate level circuit for the adder. Then when it comes to sequential design, this is probably the most kind of complex part of the digital design. And so finding the right sequential design, optimal design is very important for a good circuit, for an efficient circuit. So you start with the problem definition. You define what are the inputs and outputs, and then you determine whether it's a synchronous design or an asynchronous design. And most SoCs nowadays are all synchronous designs with the high-speed clocks in there. Then you identify the required behavior using state diagrams. And then you pick what are the memory elements you use, whether it's a D flip-flop or a JK flip-flop. And then you get into the actual state diagram. You construct the state diagram using defining what is the state representation, state transitions, what is the initial state and what are the outputs. So this is a simple picture of a state diagram, how it looks like. Then you actually minimize and optimize the state diagram. And then next step, you design the flip-flops that go into the design. And you write the excitation table and you design the output logic. And output logic is again combinational logic, and we've seen earlier how it is done. Then final step, you have to optimize the whole thing as much as possible to use the minimum number of gates. We already talked about Carnot maps and how it is done. And final step is to verify the design. You have to simulate it and make sure it is meeting your functionality and also performance requirements. So if you take a step back, 20 to 25 years ago, most of the digital design was done on a computer using a schematic capture. So you go, once you develop your circuit, you kind of graphically enter that into an EDA tool. It used to be called schematic tool. And then you extract a netlist out of it, and you simulate it in SPICE. That used to be the most popular simulation tool those days. And we still use SPICE for analog design, but those days most of the digital circuits also were done in SPICE. And then you simulate it until you reach the performance you get, and then you release that to the layout. But fast forward, we started using something called RTL language to design the digital circuits. So RTL stands for Register Transfer Level Language. People also call it behavioral language. So basically, it's a high-level hardware description language. It is used for designing digital circuits and also model the digital circuits to simulate it and make sure it meets your behavior functionality. So the advantages are it's much faster. The simulations are much faster than SPICE simulations, and your verification times also much faster. And most importantly, RTL language gave the designers the ability to handle millions of gates. So if you look at the current generation SoCs, each SoC may have millions and millions of gates, some of them more than 100 million gates. So here is a quick example of an RTL design and how it is converted that into a gate level netlist. So if you look at the RTL code, it is very similar. It looks like almost like a C program, and with inputs and outputs to your design, and the functionality of the design is captured in there. And you take that RTL code and feed that into a synthesis tool. And so we'll come back later and talk about how synthesis is done. And the synthesis tool converts that RTL code into a gate level netlist. So this is much, much faster than what you've done earlier using the schematic capture and Carnot maps, truth tables, and all that stuff. So you can see how the RTL design transformed the complete, design methodology and design cycle of an SoC. So after the RTL design, the next most important thing in the design cycle is verification. So basically, you have to make sure your RTL meets the specification and the functionality of what you're trying to do. So RTL verification starts with specifying the test plan, and basically you have to understand your design specification and create a test plan. So after that, you have to develop the test bench that is used for simulating your design. So it starts with a test bench basically includes stimulus generation. So it's a process of generating input signals. We call them stimulus for the design and the test. Then test bench includes checkers. Basically, these are the things that check the output of your simulation to make sure whether the results are expecting as they're supposed to be. And then the monitors, scoreboards, these are all different things you learn during your verification course. And once while you're simulating this design using your test bench, you have to monitor the outputs, and you have to use debugging tools, and then see if it's not meeting your, if the simulation is failing and the output is not meeting the expectation, you have to go and identify the issue and fix it. So in the industry, the typical, the most popular verification EDA tools come from, EDA companies like Cadence, Synopsys, Siemens, and the names of their tools are, VCS, Model Sim, Questa, and then you also use debugging tools like waveform viewers, assertion checkers. System Verilog has become very popular for the verification. And but as I said, the RTL design process includes, writing both RTL code and synthesizing that into a gate level netlist. We will talk about synthesis more in detail later. And once you convert the RTL into a gate level netlist, you have to do a gate level simulation again using the same test bench, and to make sure that the functionality is still intact and it is meeting the original spec. You can also, there is also, tools called equivalence checking. So you can take your RTL and do an equivalence checking with your gate level netlist to make sure that the performance is not affected, the functionality is not affected when you're converting your RTL into a gate level netlist. And the next step after the RTL design is done and verified, it meets your functionality and meets your spec. Then you have to convert that into a gate level netlist that is called synthesis. So we'll get into a little bit more in detail what this logic synthesis is all about. So when you're converting the RTL into a gate level netlist, basically it needs to be targeted to the actual hardware implementation. So are you actually building an FPGA, taking this design and implementing it on an FPGA to realize your SoC? Or you build an ASIC, a custom ASIC, to actually fabricate it and supply to your customers. So if it is an ASIC, if it is an FPGA, typically people use Xilinx and Altera. There are two of the most popular FPGA companies in the world, and they got acquired by AMD and Intel in the recent past. But if it is an ASIC, you start with identifying the foundry. Is the SoC going into a TSMC 28 nanometer process or a 5 nanometer process? And once it is targeted towards a particular foundry, and what are the libraries you're using for the synthesis? So basically, when you're converting that into logic gates, inverters, NOR gates, NAND gates, flip-flops, you're not designing those cells from scratch. So there is an existing library of cells you tell the synthesis tool to use. Similarly, memories. So most EDA companies, IP companies also supply the memory compilers. TSMC has its own memory compiler, for example. And these compilers you can use to create the memory blocks you need. If you need a single port, 1 megabit SRAM, you can use the memory compiler to create one. Similarly, IOs, you need input pads, output pads, power and ground pads, bidirectional pads. So you will have a library of IO cells. And we talked about custom cells. You can create your own custom cell and add that to your synthesis library. So this is how the synthesis step works. The logic synthesis is the EDA tool, and the inputs you give to the tool, it's RTL code you have developed and verified. Then you also create a constraints file and give it to the tool as an input. So this constraint tool defines all the clocks that are in the design and how fast they are running. And then it also talks about any exceptions like multi-cycle paths you have in the design. It talks about any constraints other things you have in there, and talks about any power and area requirements. And so this is the constraint file. You feed it into your logic synthesis tool, and then you specify your target libraries, which library of cells you want the tool to use. And then you run the synthesis tool that generates the gate level netlist. So the most popular EDA tools in the industry today, Synopsys Design Compiler and Cadence Talus. So here is a quick example here, and if you look at the RTL code of a simple 3-bit adder, it has simple description of the design. You don't have any schematic here. It's all defined in a simple RTL code, C-like language. And you feed that into a logic synthesis tool, and you're getting the gate level netlist, which is also in a text format, not like a schematic format. So you can see how the whole design cycle is simplified compared to what you were doing earlier. You starting with a truth table, Carnot map, and taking a schematic into an EDA tool, simulating it to see whether it meets your functionality or not. So here everything is simplified using EDA tool flows. The next step in the design is DFT. It's called design for test, followed by physical design. But let me skip DFT for now and talk about physical design, and I will come back and cover the DFT as the next step. So before we get into physical design, let us understand the timing concepts a little bit. So when you are taking a gate level netlist and convert that into a physical design, you have to make sure it meets the performance requirements. And the most important thing is the speed at what the design will be running at. So let's say if you are designing a chip that's running at 1 gigahertz, then you define your clock with a clock period that meets that requirement. And after converting that gate level netlist into a physical design, so the physical design will have the interconnects between these gates, and that will introduce parasitics, and it will introduce delays between the gates. So the first thing you need to understand is what is a setup time. So basically it is the window of the data that needs to be stable before the edge of the clock. So basically if the data is going from one flop to another flop, so it has to be stable for a certain period of time before the clock's edge. Similarly, the hold time. So it is the amount of time, the window of time the data needs to be stable after the clock edge. So these are just some basic timing concepts you need to understand during the physical design. And here is a typical physical design flow. So this is probably the most complicated or time consuming or resource consuming step in the design process, The EDA tools used in this process are quite complex. You need extensive training in using those tools, and you need the tools are expensive, and you need a lot of computing resources as well during this process. So you start with importing the design into your EDA tool. Typically, we call them place and route tools. And you go through the floor planning and power planning, place and route, and then you make sure it meets timing, and then you do the physical verification. So I'll go through the key steps in the process, and that will give you an idea of the whole physical design flow. The first step in the process is floor planning. You can kind of compare that or analyze that like a typical floor plan you create. I'm comparing that with the floor plan you do when you're building a home, for example. So you have to decide where your master bedroom is, and where your bathrooms, where your kitchen, and where is the entrance for the house. So similarly here, you take all your key blocks in there, and based on how data they're connected and how the data flows, you decide where these blocks are placed in the design. And then you define your I/O ring, where the inputs to the chip are coming from, where the outputs are going, and then also you have to decide, the chip, the most important thing is chip needs power and ground supplies, and where these power and ground inputs are placed in the chip. And as part of the floor planning, you also define the power and ground mesh, a network in the chip. So you need every component in the chip needs power and ground, and you have to make sure that it gets enough power. So let's the power signal is power source is coming from the periphery of the chip, and if your component is in the middle of the chip, you have to make sure that the power drop from the periphery to the center will not affect the performance of the component. So you have to make sure it meets IR drop requirement as well. So you build a power mesh, and you kind of, there are tools you can use to analyze that power mesh to make sure that the IR drop is within the limits. So these are the two most important aspects of power planning. Placing all the cells in the design, on the I/O ring, designing the I/O ring and power mesh to make sure that you have a good start in completing the floor plan, completing the place and route. Then the next level is placement optimization. So as I mentioned, we are building these SoCs with millions of gates. And if you look at closely in this picture, these cells are placed in rows, and you don't do this manually. You use automated tools that will go and place these cells based on their connectivity and based on the timing requirements to optimize the interconnects between them. And then you post, it's an iterative process, and you keep iterating, optimizing the placement to make sure it meets the performance requirements. And the next step is in the physical design is to build clock trees. So let's say you have a clock signal coming from the periphery of the chip, and it's driving thousands or sometimes millions of flip-flops in the design. You have to make sure that the clock insertion delay, the time it takes from the periphery to reach the flop, it's the same thing for, it is within the limit for, when it reaches every flop in the design. I'm kind of simplifying things a little bit here. And so there are two terms you need to understand here when you're building the clock tree. One is the insertion delay and the clock skew. So basically the skew refers to the variation of the clock delay between different flops, and you'll be learning more about these things in the actual physical design webinar. So once you have the placement and clock tree in place, then you have to start connecting these signals with the actual metals. And the current, day, let's say if you're designing a chip for a TSMC, 5 nanometer process, you may be using, more than 10 layers of metal stacks to connect these gates, and it's all done automatically with the place and route tools. And again, the tools kind of keeps iterating and keeps changing the routing and finding the optimal way to connect them to minimize. So the overall, the goal is to minimize the routing length between these gates without creating any shorts or opens between the cells. And so here, let's say you start with a gate level design. Functionally, it looking good. But when you actually take the design and convert that into a physical format and connect the cells using metal layers, the metals will be introducing some parasitics between the gates. So basically, it will introduce some additional capacitance and resistance, and so that will create the signal delay going from the output of the previous cell to the next cell. So you have to take these signal delays into account to make sure that your design meets the performance requirements, the clock speed, and meets all those setup and hold time requirements. So you take this physical design and extract all the parasitics of the interconnects and feed them into a static timing tool. So here, kind of you get an idea of how this static timing analysis works. You extract the gate level netlist from place and route. That includes the original gates and all the clock trees you inserted. And you extract all the parasitics of the interconnects and feed that into the tool as well. And then you have to define the constraints. This is a constraint file that will have the clock speeds, the input delays, output delays of each input to the design, and then you also define, there may be some paths, sequential paths in the design that may be multi-cycle or false paths. There may be some exceptions. So you put them all into a constraint file and you feed that into the tool. And then you run the tool to analyze the results. So the tool will give you an output. To begin with, it says, okay, the design is meeting timing or not meeting timing. Or if the design has some violations where it's failing the setup time and hold time requirements. And so it gives you an output file that you can go through and analyze the results and identify the problems and generate ECOs to go back and change the design, fix these problems to make sure that the design meets the timing. Again, it's an iterative process, and there is, people talk about physical design that takes RTL netlist and gives a clean GDS2 in one go. But in reality, it doesn't happen. It is an iterative process, and the engineers have to go through multiple iterations to get a clean physical design out of the netlist. And the most popular EDA tools for doing static timing is, they are from Synopsys, PrimeTime, Cadence, Tempus. And once your design is converted into a physical layout and it meets your timing, the most important thing again is to make sure that it meets your foundry guidelines. So one, it needs to meet the design rules. So every foundry will provide these rules for a particular process. For example, if it's a TSMC 28 nanometer, the foundry will tell you what is the minimum width of the metals you need to use, width of the spacing between the metals, and how big your vias need to be, interconnects between the metals. So it's a very complex, there will be very complex design rules, and there are tools out there that will take your layout and run these checks and tells you whether it meets the requirement or not. The most popular physical verification tool in the market today is Caliber from Siemens. And also during the physical layout process, if you short any metal layers or if you leave any opens, this tool will also run a layout versus schematic check. We call that LVS, to make sure that your layout actually meets the gate level netlist. It is also very crucial. You don't want to send a layout that has opens or shorts in your design to the fabrication. In the earlier step, we talked about physical design, but as I mentioned, let's go back and talk about the DFT, because it is also a very crucial step in the design process. Why DFT? DFT stands for design for test. See, once you design your chip, SoC that has millions of gates, you fabricate it. You want to test it thoroughly that it doesn't have any bugs or any defects, manufacturing defects, and make sure that it meets the customer requirements before you actually ship it to the customer. So there are two ways you can test the chip. One is the functional test. So basically you create some test patterns based on the functionality of the chip, and you observe the outputs to make sure you're getting the desired expected outputs or not. And but again, to test every functionality of the chip, it can be very time consuming, and you probably have to generate millions of use cases to check the functionality of it. So it's a very time consuming effort, and takes a lot of time. So people it takes compute resources, but people will still need to do some functionality test before they release it to production. And then there is another form of test is for the structural defects. Let's say you're taking your gate level netlist and convert that into a physical layout. We've seen that, and now the layout meets all the DRC LBS as specified by the fab. But during the fabrication process, the wafer may have some defects. So basically the defects can create shorts or opens in the design. And so once you get the silicon, you have to test it thoroughly to make sure that every gate and interconnect in the design is intact and there are no manufacturing defects on it. So to do that, you create certain test patterns, and run these test patterns on the chip on a tester and observe the outputs to make sure whether chip is failing or passing the test. So here, it gives you an idea about the manufacturing defects. And let's say the two metal lines running parallel to each other, if there is a short between them, it can, create a problem, and you may have to throw away the chip. Similarly, during the process, it may create a break in the metal line, and it can be an open. So how do we, handle these things while you're testing it? So basically, we use fault models. If it is a short, it can be like a stuck at fault. If it's an open, it can be, stuck at 0 or stuck at 1, we call it. And then there are transition faults in the design. So basically, you create some fault models, and you kind of create a design for test type of methodology to detect these things on the tester. So basically, these tests they compare the predicted behavior of the gate list to the actual silicon, and make sure that the chip is built as designed, and the chip is not, has some defects in it. So the idea is to minimize the delivering, actually not minimize, avoid delivering any defective parts to the customers and obtaining the maximum yield from your manufacturing. So when I say yield, let's say your wafer has 1,000 chips in it. In real world, not every one of them will work. You may have to throw away some chips in it. So that is called yield. Let's say you have every 100 chips, you're throwing away 2 chips, for example. That means you're getting 98% yield. So you will never get 100% yields, but you have to maximize your yields as much as possible. So how do we do this? People come up with this methodology, this DFT methodology. Basically, they replace every flop in the design and with a scannable flop. And so you will kind of understand this more in detail during the webinar on DFT. It is a complex process, but I'll just give you a quick overview of it, very high level. So as I said, you replace the normal flops with scannable flops, and you stitch them together like a chain. And then you generate some patterns and send them through these chains from the input to the, and then you observe the output of the scan chain. And that will tell you whether there are any defects in that particular chain, and it will tell you whether it's passing or failing. Similarly, if you have a memory block in your design, and if you have let's say you have a 1 megabit of SRAM block in the design, and if there is one memory cell is not functioning, then you can throw away the whole chip. So people come up with a methodology to add some redundant cells in that memory block. And then there is the MBIST, they call it. It will automatically do a self-test when you bring up the chip, and it will detect any defective memory cells in there and kind of replace them with redundant cells in the block. So this is called memory built-in test, MBIST. And you also have something called boundary scan that will check your, IO ring and make sure it is all connected, functioning properly. So so this is the DFT, step you go through and insert this DFT into the netlist. Actually, you get into the physical design. And when you actually doing the static timing on the chip, you do that in two modes, one in the functional mode, one also in the DFT mode. The next step in the process is to send your physical design database to a fab. Basically, we release that to a fab to start the manufacturing of the chip. So, I'll give you a very high level overview of what happens in a foundry. But before we go there, this is an interesting, picture. People, I want every semiconductor engineer to understand this. So basically, you start with a logic gate. For example, it's an inverter, and how it looks like in a schematic form. It has a PMOS and NMOS transistor in there. And then how it actually, the physical cross-section of the CMOS inverter looks on a wafer. And but to manufacture that, you actually need a mask with different layers in it. And so if you look at the layout here, it has a poly gate and N plus diffusion, P plus diffusion, and the metal, metals connecting it to the transistors. So it's kind of, important to understand the correlation between the mask description of the inverter and the actual cross section. As I said, it is a very interesting picture, and every semiconductor engineer should try to visualize and understand this. So when actually it goes into the fab, so there are multiple steps in the fab that keeps getting repeated to create the structures in the wafer. So some of these key words you can understand, I'd like you to, at least get a good feel for them is one, oxidation. So basically you grow a layer of silicon dioxide on the wafer, which is used as an insulation between the transistors, and also silicon dioxide is used as a gate material. So basically when you have a gate that has silicon dioxide and polysilicon on it, that will be used to power on and off a transistor. Then the photolithography. So basically it's a process to create different patterns on the wafer to identify where to make your deposits of metals, for example, or make your implants, for example, N plus implant or P plus implant. Then etching is a process. People use chemicals to create etch these layers. People also use something called reactive ion etching. I won't get into those details. And deposition is used for creating metals. As I said, implantation is used for creating these, N plus, P plus areas within the chip. So it's a simple, thing I will just, give you, just to give you an idea how an anvil is created. So you first create a layer of oxidation on the wafer. Then using the photolithography process, you remove the area where you want to create the anvil, and then you implant it with N plus diffusion. That will create the anvil there. Then you similarly create gate oxide and polysilicon to create the gate regions for the PMOS and NMOS transistors. Then you implant P plus and N plus to create the source and drains. And then you go through the metal depositions to create the interconnects between them. So I kind of given you a very high level overview of this. In fact, this is a very complex process, and if you go through, if you look at probably the 5 nanometer process at TSMC, it may be going through, hundreds of these steps to get the final silicon wafer. And so once you fabricate your chip and get the wafers back from the foundry, then you actually have to bring them up in the in a lab to make sure that it's functioning properly, and test all the corner cases and see whether it's ready for production release, volume production. So this step is typically called silicon bring up and validation. So during this process, you bring up, power up the chip in the lab, and you test the functionality to detect any bugs. And also you test the functionality in different operating conditions. For example, different temperatures, you look at how the voltage variations will affect the chip. And also make sure all the interconnects are working. If the chip is has a DDR interface or a PCI interface, make sure all those interfaces are functioning properly. And also you actually load your software on the chip and make sure it is working well. And then once it works in the lab, then you also want to make sure that all your DFT patterns you created, your scan patterns, your MBIST patterns, all those stuff are working well on the tester. So you put this chip on the tester and validate all those vectors before you release it to volume production. Similarly, you have to, in case if the chip is used in automotive applications, it might need some qualification, auto grade qualification. Similarly, if it is used in space applications, it may have more, demanding qualification requirements. So basically, after the, getting the prototypes from the fab, you bring it up in the lab and validate it before you release it to volume production. And I will also talk a little bit about OSATs and or ATMP, you call it. OSAT stands for Outsourced Semiconductor Assembly and Test, because India is investing heavily in these things now, with the latest semiconductor policy from the central government. So once you fab the chip, it comes in a wafer form. It's a big round 12-inch wafer, and each wafer may have thousands of chips. You can see each square in this wafer is a chip, and then you cut them into individual chips and package them into, put them in a package before you ship it to the customer. The package serves multiple purposes. One, it connects the chip to a, let's say PCB. So ultimately, if you, have to mount this on a PCB and, solder it there. So package serves as the, interface for the actual silicon and the PCB. Then it will also, when the chip is actually operating, it will be generating heat, and it will protect the chip, the silicon from the environment, and also, it will dissipate the heat generating out of the chip. So there are typically two types of packages, most commonly used package. You connect the die to the package using wire, gold wires. Typically they use gold wires. And or you actually flip that die and directly solder that to a mini type of PCB. We call that substrate, and that will use that is acts as the interface between the die and the PCB. So that is called flip chip. So these are two terms you can try to remember: wire bond package and flip chip package, most commonly used packages in the industry. And so this is the whole process. Once the wafer comes back from the fab, the first thing you do is wafer level testing before you cut them into individual dies. So basically you use a probe card that goes and sits on each chip and sends some test vectors to the chip and observes the output to identify the defective chips. So you don't want to take a defective chip and package it because you'll be wasting money. So once you identify the defective chips, you throw them out. You dice the wafer into individual chips, and then you throw out the defective chips, and then you package them and do another final test before you ship it to your end customer. So this whole process is called OSAT, Outsourced Semiconductor Assembly and Testing. So this is a detailed step-by-step process what happens in an OSAT, and I won't go into the details on this. So in summary, semiconductor industry is growing at a steady pace, and it is expected to reach $1 trillion by 2030. Because every device you use nowadays, whether it's your TV or whether it's your car, whether it's your smartphone, everything needs semiconductors in there. Even your lighting, it needs, all the LED lighting needs semiconductors. So the job opportunities for semiconductor engineers is steadily growing. Today, I believe India is hosting the largest number of chip design engineers in the world. And it starts with, RTL design engineers. These are different job titles you can find in the industry. RTL verification engineers, so you can be a verification engineer for your entire career, just running verification on the chips. Similarly, DFT, physical design, SOC architect, package design engineers, test engineers, process engineers, and analog design. This is again a complex, expertise that's required. Analog layout and product engineers and application engineers. So the demand for these engineers is steadily growing in India. And to get in there, definitely you need some hands-on training, and it can come through do a master's degree or through an entry-level position in a company, or even through taking some hands-on training in one of the institutes in India. With that, I thank you all for giving us this opportunity to do this webinar. I hope all the students will benefit out of this, and I wish you all good luck.